And thanks to all of you for showing up. Yes, I'm Nishad. You can just call me Nishad. No need to add anything else if you feel comfortable. And please interrupt me whenever you have any questions. Right? Yeah. So I would like to tell you about the four-color conjecture. Well, now a theorem. So how many of you, just to get some sense of the audience, how many of you have never heard of the four-color conjecture or theorem? Um, you can type, you can turn on your mic, whatever you like. Okay. Since nobody is saying, I'm assuming everybody. Okay, good. Okay, you have heard. Okay. Cool. Yeah, you can type also. I'm listening. I'm looking at the type messages. Um, yeah. So you have heard. I haven't. I haven't. I haven't. Great. Excellent. So let's start with the four-color conjecture. Right. So today's part is going to be mostly historical, and I'm going to do two parts. So you will see real math quite soon, but of course, real math starts with very basic things, right? And now we are going back to 1850s when this was probably not as basic. So I want to just read out to you a letter from D. Morgan, the same D. Morgan of set theory laws, right? Most of you probably know of D. Morgan's set theory laws, right? So this is from 1852-53, and this is what D. Morgan writes. A student of mine, U3. So these are two possible people. They are both brothers, Francis and Frederick U3. I hope I'm spelling the names correctly, but anyways, they both did PhD with D. Morgan. So it's hard to tell which U3 they are referring to. But anyways, so U3 asked me today to give him a reason for a fact which I did not know was a fact and do not know yet. He says that of a figure. So look at the math. Look at how um, look at how informally it is stated. Like today's modern mathematics, this would just not be acceptable. Right? So if a figure, what is a figure? I don't know. Let's try to guess. This is a figure, maybe. If a figure be anyhow divided and the compartments differently colored. Okay. So let's divide it in some way. Um, right? I'm trying to guess what this person is saying. But of course, there is a lot of history. So, okay, so this is a figure, and I have divided it by drawing lines. My drawing is not great, but that's okay, hopefully. Be anyhow divided, and the compartments. What is a compartment? They never really defined it. So maybe this is a compartment. This is another compartment, right? This could be what they mean. Um, and the compartments differently colored. So you want to color the compartments so that figures, they should really be compartments, but they wrote figures. So that compartments with any portion of common boundary line, this word is really important. If two compartments have a common boundary line, like compartment 1 and compartment 2, then they should get different colors. They are differently colored. So if I color one of them red, then the other one cannot be red. It should be blue, green, whatever. Yeah. But observe that this is about a common boundary line, not a common boundary point. For example, I could make a compartment like this. Now observe that compartment 1 and compartment 3, they have a common boundary point, but it is not a line segment. It is just one point. So I could give the same color to compartment 1 and compartment 3. However, compartment 2 shares a common boundary line with compartment 1 and also shares a common boundary line with compartment 3. So 2 should get colors different from 1 and 3. However, 1 and 3 could get the same color. Okay, so this is crucial. The line, it is not a point. 4 colors may be wanted, but not more. So what they are saying is that you may need 4 colors, but not more than that. The following is his case. I'm going to skip the case. You can draw that later yourself. The following is his case in which 4 colors are actually wanted. Query cannot. Look at this last line. It is really poetic. The last line says, query cannot, a necessity for 5 or more, be invented. What they are saying is that you cannot create an instance where you actually need 5 or more colors. They are saying that 4 colors always suffice. Okay? So the last sentence is basically saying that 4 colors suffice. You will never need more than 4 colors to color this region, all the compartments, so that any 2 compartments that share a common boundary line, they get different colors. And this is what eventually became the famous 4-color conjecture. And today it's famously known as the 4-color theorem. And between becoming a theorem from a conjecture, it took 124 years. Okay? So it finally became a theorem in 1977. And the conjecture generally is attributed to Guthrie, 1853. 52, 53. Yeah, one of those years. Right? Yes, this is one of the first mathematical results where computers were indeed used in the proof. Somebody put a comment on the chat. So yes, that is true. I will come to the history. All right, but is the statement of the problem clear? Of course, it's not very precisely mathematically stated. Right, today in modern mathematics, this would basically be thrown out. But let us not judge 1853 by the standards of today. Right? And what I want to do next is I want to convince you all that this is basically a statement in graph theory. Yeah? Okay. So that's what we will do next. We will make sure that we see why this is actually a statement in graph theory. Are there any questions or concerns at this point? If there are, please interrupt me. Okay. So if it's okay, I will probably erase this part and just focus on this drawing here. Yeah. So let's see how I do this. Okay. Okay. Great. Let me remove this. Okay. And let me just recall that it was finally proved in 1977. Okay, and let's take this fellow and move it here. Okay. And let me just erase a few things here. It's a bit messy. Okay, redraw some things. Okay, good. Fine. So this is our figure that we divided into so-called compartments. And now I want to convince you why this is really a statement in graph theory. Maybe one of you can try. Can somebody try to tell me how do I convert this creature into a graph? And there might be multiple ways to do it, but let's see if we can get one way to do it.
Maybe consider the compartments as a vertex,
Okay.
like connect to compartments if they set a boundary.
Sure, that is one way to do it. And actually, I will get to that very soon. But can we see an even more basic way of turning this into a graph theory problem? So we will see multiple ways of doing it. And the one that you just stated, we will come to that in a few minutes. Any other more basic ways of doing it? Denote compact ends as vertices and joins ones which share a boundary. Yes, I think that is along the same lines that somebody else mentioned. Is there any other way to do it? Can you do something more basic than that?
Maybe just take intersection points as vertices and the lines that join them as edges.
Yeah, exactly. So that's what I'm going to do. Thank you. So that is the one I was looking for. That in some sense you will see is a more basic thing than the other ones which are more sophisticated. So yeah, that's exactly what I'm going to do. I'm going to think of all of these. Maybe I'll use a different color. Maybe I'll use pink. So I'm going to think of all of these intersection points as vertices. Okay. I'm not going to be super rigorous about it, but okay, hopefully you get the idea by this example. I will think of all of these as vertices. Oh, sorry, we don't need that. This, this. Okay, did I get all of them? Yeah, I think I will put one more here. Yeah, actually, I'm going to put a few more. No, actually, I'm fine. I'm good. I don't need that last one. Okay, good. So these are my vertices. The pink colored things you see are the vertices of my graph. All right. Let me know if I missed anything, but I think I got all of them. Okay. And what are the edges of my graph? Well, the edges are exactly any green curve that joins two pink points. For example, I'll use yellow maybe to show an edge. This is one edge, or maybe yellow is not so clear. Let me use, I don't know, orange, some kind of orange. This is one edge of my graph. This is also one edge of my graph. So is this. So is this. And so on. Yeah? Is that clear? Do you all agree that we have a graph? I have not colored all the edges.
Yes.
Okay, good. In fact, I will now remove the things I colored, the edges I colored. Okay, so you get the edges and you get the vertices. And now the question is, what are we coloring? We are not coloring the vertices or the edges actually. Right? So we are coloring something else, which is not really a graph theoretical concept. It is not an abstract graph theoretical concept. I will try to make this point clear. So what exactly are we coloring? We are not coloring vertices or edges.
The
What are we
bounded
coloring?
region. The
Sorry.
bounded region by the vertex.
Bounded regions, yes. So you are calling them the bounded regions. I will use the modern term today, faces. So these are called faces. But you can't talk about faces of a graph in general, can you? Does a graph have faces?
No.
No, right? But this graph has faces. What is so special about this graph? For example, can I talk about the faces of this graph?
Yeah.
Of course, you can define it in some way, but this seems quite different from this, right? So
Not
what
exactly, because there are intersections which are not vertices.
Yeah.
exactly. Here the vertices are these 5 vertices, and the edges are the line segments joining any two, right? So 5 choose 2. I have 10 edges. And the point is that there are places where these lines are intersecting that are not actually vertices. This is not a vertex of the graph. However, here, the way we define this graph, that doesn't happen here. Whenever two lines meet, it's basically because there is a vertex at that point.
That's like we are marking vertices. That's
Sorry, there.
like we are marking vertices wherever like two lines.
Exactly. That's how we draw the vertices and the edges. That is how we define the vertices and edges. So this kind of a graph is called a planar graph. Okay, and I'll give you the formal definition. But what we have is not just a graph. We have a planar graph. In fact, I'm going to use another word called a plane graph. Okay, and I'll explain everything. I'll explain all the differences. So what we have here is a plane graph. By plane graph, I mean it is a drawing of a graph in the plane so that whenever two edges meet at a point, that common point is actually a vertex that is a common end of those two edges. And you can see that that is happening here. If you take any two edges that meet at a point, let's say I take one blue colored edge and I take one orange colored edge. They are meeting here, but this point is a vertex that is a common end of these two edges. Okay, so this is what I mean by a plane graph. It is a drawing of the graph, right? So I'll just write down. This is a drawing. The more modern term these days is embedding. It is an embedding of a graph. A graph itself need not be drawn. Here we are the audience members in this call or in this meeting, and you can define a graph. All of us are vertices, and there is an edge between two of us if we know each other from before this video call started. Right? And this is a graph, you don't need to draw it, right? So, in that sense, when I say plane graph, I mean the drawing of a graph in the plane R2. In the plane R2, such that whenever two edges meet, so they meet at some point, that point, such a point, is a common end of those two edges. Yeah, I think it's clear, right? If there are any
Basically,
questions,
can we say they are mutually exclusive and exhaustive type kind?
can you repeat that?
Like if every phase is considered as a set, then all the sets are mutually exclusive and exhaustive. Can we say?
Yeah, so I haven't really defined a face yet, but yes, what I will define faces as well. But essentially, if you remove, in some sense, one way to define a face of a graph is you remove the drawing. You somehow, I'll give an intuition. Take the drawing of your graph on a piece of paper, right? A piece of paper sort of simulates the plane. Now you cut out your graph. Wherever your graph is drawn, you use a pair of scissors to cut it out. And the pieces that fall apart, those are the faces of your graph.
Okay.
Right? And if you put them all back together, you will get the original thing. So in that sense, they are indeed mutually exclusive and exhaustive. I think that's what you mean. Yeah.
Yeah.
So any two faces are disjoint. And if you take the union of all the faces along with the graph itself, you will get the original plane.
Okay.
Yeah. Okay, cool. So anyways, coming back to a plane graph, this is what I mean by a plane graph. It is a drawing of the graph in the plane with this property. Now, the moment you see this, a natural question is, for every graph, can I draw it in this way? Is it possible to draw any given graph in this manner?
If the edges are not sufficient, then I guess not.
Edges are not sufficient. Can you explain that a bit more?
Like if there is a graph such that only there are two vertices and a line, then but there will be one face still. Like
Okay,
the
so
example you gave is also
this one?
yes.
This is a famous graph called K5, and one can prove that this graph cannot be drawn in this manner. Okay. I'm not going to prove it today. Right? So if you want, I can talk about this another time. But today I'm going to just give you as an exercise to convince yourself that this graph cannot be drawn in this manner. But now I'm going to introduce to some definitions so that I don't have to say so many words every time. So whenever I can draw a graph in this manner, I will call it a planar graph. Okay. So this is the plane graph. And now I'm going to define what is called a planar graph. Planar graph is any graph that admits, by admits I mean for which you can make a drawing that admits an embedding with this property. Whenever two edges meet, they meet at a common vertex. Okay? So this graph, of course, this is a planar graph also because I have drawn it like this. However, this K5 is actually not planar. So I'll give this as an exercise. Do it yourself. Convince yourself, not now, maybe later. Convince yourself that K5 is not planar. You cannot make a drawing of K5 where this property holds. In any drawing of K5, you will always have two edges crossing in a place where they shouldn't really cross. A tree is planar, that's right. Tree is planar. That is, tree isn't planar either, right? No, trees are planar. Yeah, that is a point we will use later. All trees are planar. So another DIY based on the chat. All trees are planar. For every tree, you can make a drawing with this property. Okay? And just to be clear, a tree is any graph that is connected and does not have cycles. Probably most of you know this. Okay? Good. So what we get from the original problem posed by U3 is a plane graph. And now to actually state the 4-color conjecture, we need to define the faces of the plane graph. Okay? And I'm not going to write down a formal definition. I'm just going to go with the intuition that if I cut out my plane graph from the plane, if I remove the graph from the plane itself, then the plane actually breaks into pieces. And those pieces are called the faces of your plane graph. Okay, let's do a small example and count the number of faces. Okay, this example is too big. Let's do a smaller example. Let's see. Here is a nice graph. Can someone tell me how many faces? This is the plane graph. How many faces does it have?
6.
6. Yes, there are 6 faces. Let us quickly mark them. 1, 2, 3, 4, 5. And there is the outside face. Yeah, the outside face is also a face. All right. And what U3 said, what U3 conjectured, is that you can color all the faces. Actually, U3 did not care about the outside face. So I'm going to make a stronger statement, slightly stronger. Turns out this is also true. So the stronger version is that for any plane graph, you can color its faces using 4 colors. So that whenever two faces share a common edge, remember that boundary line point? So now that line is becoming an edge, not a vertex. Whenever two faces share an edge, they should receive different colors. And U3 conjectured that you can always do this with just 4 colors. Yeah. And this statement that is in principle so easy to explain, like you can explain to a 5-year-old kid this statement by just giving them a coloring book and giving them a bunch of figures and asking them to color, right? They will get the point. You don't need to use all this terminology, right? And this very innocent statement took 124 years to be proved. And even then the proof was controversial because of the use of computers. I'll come back to that history, right? So that's how innocent this statement is, and that's how difficult it is to prove. Welcome to combinatorics. Any questions, concerns? Okay. Kind of like Collat's conjecture, yeah. Hmm. Collat's conjecture is very cool. Okay. Okay, so what we will do next is we have seen one version of the four color conjecture. I'm going to actually write it down more formally, but without using without defining too many things that I have already kind of defined in some sense. So one way to state the four color conjecture in modern terminology is as follows. The four color conjecture. I will keep using the word conjecture and theorem interchangeably just because I'm taking a more historical perspective. And for 124 years at least, this was indeed a conjecture, right? So it states that every plane graph is four face colorable. Okay. And the whole non-trivial part is hidden in this word. Four face colorable means color the faces using at most four colors. You don't even have to use all the four colors. Right? You could not use some color maybe in some graphs, in some plane graphs. But you can use at most four colors and color the faces such that whenever two faces share an edge, they get different colors. Yeah. So this is the four color conjecture. All right. So what I want to do next is I want to give you equivalent versions of this conjecture. And one of those equivalent versions is basically going to be along the lines that some of you suggested. When I said let's transform this problem into a graph theory problem, some of you gave a different way of looking at it. So that we are going to formalize. Yeah? Okay. Any questions or concerns? If not, I will erase a few things and then explain the other formulation. All right. So So this is one version. This is called the face coloring version. The problem with this version is that you need a plane graph. Because to talk about the faces, you need a plane graph. You can't talk about the faces of an abstract graph. By abstract graph, I mean a graph. Right? For example, when I say K5, I just mean K5. I don't mean any specific drawing of K5. Right? So this requires you to have a plane graph. Turns out we can do something interesting. So let me draw a plane graph. Maybe I will draw the same graph again. Why not? Okay. Here is a nice plane graph. And instead of coloring the faces, what we will instead do is we will construct another graph on top of this graph. And then somehow coloring the vertices of that graph will become equivalent to coloring the faces of this graph. Right? Of course, we'll have to define what we mean by coloring vertices, what is the condition that should be satisfied, right? But before we get to coloring, let's just think about how to get another graph from this graph. And this is exactly what some of you suggested. Put a vertex inside each region, what we earlier called compartments. Inside each compartment, place a vertex. So this yellow graph I'm drawing is a different graph. Okay, the white graph is G. The white graph is G, and the yellow graph I'm drawing, I will call it G star. Okay.
So shouldn't
And
there be another vertex?
sorry.
Shouldn't there be another vertex?
Yes, there should be. You are right. The outer face also is a face, and therefore I also need a vertex in the outer face. Thank you. And now what we will do is, now we will define the edges of this yellow graph. So can anyone tell me how we are going to define the edges?
If they share a common boundary.
Exactly. For two vertices of the yellow graph, I will look at the corresponding faces of the original plane graph. And those faces, if they have a common edge in the boundary, then I will put an edge between the two yellow vertices in the yellow graph. Okay. So here are two faces of the original graph that have a common edge in the boundary. So I will put an edge like this. And I will do this for every white edge. I will draw a yellow edge crossing that white edge. Yeah. Good. And now the graph I have, it's called the dual of the original graph. It is called the dual. Dual of G. And observe that if you color the vertices of the dual, so that any two vertices that have an edge joining them in the dual graph, they get different colors, then that is basically also it is also a valid face coloring of the original graph. Right? So two faces are adjacent in the white graph. Adjacent means they have a common edge. If and only if the corresponding vertices are adjacent in the yellow graph. And now adjacent means there's an edge joining the two vertices. Okay, so I'll just write down the summary. Coloring the vertices of G star using 4 colors so that adjacent vertices, now we are referring to adjacent vertices, which means there is an edge between the two vertices. So that adjacent vertices receive distinct colors, or rather, let me just say different colors, receive different colors. This is equivalent to coloring the faces of the original graph. Let me use white for this. This is equivalent to coloring the faces of the original plane graph using 4 colors. Good. Yeah. Was there a question? Is the dual of a plane graph also planar? Yes, that is indeed true. Yeah, I'm not going to write down a rigorous proof of that, but I will try to give you some intuition as to why that is true. Yes. So the dual we drew, observe that this is also a plane graph. In our drawing, whenever two yellow colored edges meet, they meet at a yellow vertex. That is a common end of those edges. So the dual is also a plane graph. And we actually got a very nice plane embedding or drawing with that property, right? Yeah. But anyways, for now, let's just move on. But if you all want me to convince you why it is plane, I'll try to do that, or you can try doing that yourself. Right? And the dual is also mutual. You mean the dual of the dual is the original graph? Yeah. You just need the original graph to be connected. Otherwise, the statement is actually not true. I'll leave that as an exercise. But yeah, in general, for a connected plane graph, it is indeed true that the dual of the dual is the original graph. Okay, good. Great. But let's come to this point again. Why is this better than this in some sense? Why is
The
this?
notion of coloring vertexes is better than like coloring
Yeah.
the faces.
Yes. Why?
I mean, first, it feels like defining vertexes is better than defining faces.
You are right. I want you to make it more precise, and I want you to go to this point.
Oh,
Can
yeah.
you-
Okay, we remove the condition of a plane graph.
Now you don't need a drawing. Now you can take any planar graph, coloring the vertices being adjacent has nothing to do with the drawing of the graph. Right? So this vertex coloring version actually doesn't require a drawing. It just requires a planar graph. It should have a drawing which is planar. But the coloring of the vertices has nothing to do with the drawing itself. Right? So now I can state the four color conjecture for planar graphs rather than plane graphs. Planar graph is not a drawing. Planar graph is any graph that has a drawing with this property. Right? So let me just write it down. So now we have another version of the four color conjecture. I'll erase this point and make some space here. Let me write it in yellow. Four color conjecture. We'll keep some space. Four color conjecture. Every planar graph is for vertex colorable. And of course, the main point is captured in this definition. By a four vertex coloring, I mean a coloring using at most four colors, so that whenever two vertices are adjacent, they get distinct colors, they get different colors. Yeah, the four color conjecture is already proved in 1977. Of course, whether you believe it or not is a different matter. But anyways, we'll come to that later. So this version is called the vertex coloring version. Right? And these are equivalent. These two statements are equivalent. You prove one, you prove the other, and vice versa. Yeah. And the advantage of this one is that it does not require an embedding. You don't need a drawing. You can just color the vertices, right? You just need to know that there exists a planar drawing, right? But you don't need it in order to define vertices. Every graph has vertices, if it has a vertex. Right. Okay. Are there any questions or concerns? Is everybody convinced about this part, at least at some level? Is there a question? No?
Yes.
Yeah, go ahead.
So if there are two plane graphs which are isomorphic abstractly, are their duals also isomorphic abstractly?
Good question. No. In general, planar graph may have two different embeddings in the plane, so that when you draw the duals, those are not actually isomorphic. Let's look at an example. That's actually a very interesting question. I'll give you a graph. Here is one drawing of this graph. Let's call this G1. Can you now give me another drawing of the same graph, so that when you draw the duals of the two, those are not isomorphic? And I will label the vertices so that you can tell me what to do. 0, 1, 2, 3, 4, 5. Can you give me another planar embedding of this graph G1? So the G1 star is not the same as G2 star. Yeah, go ahead. Yeah, better.
Maybe we just reflect the vertex one across the, so that it's outside of the.
This one, right? Yeah,
Yes.
let's do that. So basically,
Over O2.
this is the same graph as, let me just select it. Okay, and now what we will do is we will simply put this reflected outside as you suggested. Yeah, this is my G2. Clearly, these abstract graphs are the same graphs, but the drawings are different. As plane graphs, they are not the same. And in particular, if you draw the dual, you will see that the dual of this fellow is not the same as the dual of this fellow. Right? You can all draw the dual and convince yourself. Good, thank you. There is, however, something really cool, but I am not going to explain that in this these lectures. So I mean, I teach these things in my structural graph theory course, which is fully available on my YouTube channel. So the problem with this graph, it is not connected enough. Remember our earlier question, is the dual of the dual the original graph? And I said you need the graph to be connected for that to be true. So connectivity somehow plays an important role. In the same sense, if you want this statement to be true, you need a notion of connectivity that is called three connected. For a three connected simple graph, any two planar embeddings will give you the same dual. So I'm just going to write this fact, but this fact is way beyond this lecture. Fact. For a three connected simple planar graph, any two, the dual is unique. Let me just say like this, the dual is unique. In other words, if you take any two planar embeddings and you draw the dual, those will be isomorphic to each other. They will be the same graph. Yeah. And just to make it clear, what I mean by simple is, in general, in graphs, I allow multiple edges, also known as parallel edges, and I also allow loops. So by simple, I mean neither are loops allowed, nor are multiple edges allowed. Okay. Yeah.
What does it mean for a graph to be three connected?
Three connected means that not only is it connected, but even if you delete any one or two vertices, it is still connected.
Okay.
Yeah. And yeah, there is a lot of theory on connectivity, but yeah, I'll not cover all of that. But yeah, so that's what three connected. Okay. Good. Any other questions, concerns? Okay. So if not, let's go back to our original point. Right, so I am not expecting everybody to follow all of that. It depends on your prior exposure to graph theory. The important point is we have seen two versions of the four-color conjecture. the face coloring version, which was the original version proposed by Guthrie, right, essentially, not in terms of graph theory, but in some other language. And the vertex coloring version that basically comes because of duality. So this is called plane duality. What we discussed here is called plane duality. For any plane graph, there is a dual that is also actually a planar graph. Right? And using plane duality, we saw that these two are equivalent. Any questions, concerns? Okay. So in order to, yeah, go ahead, sorry.
Are there other forms of duality other than plane duality?
So duality, yeah, actually there's another question also. I'll also address that. If a graph is three connected, can we say anything about the dual? Yeah, so in fact, for a simple three connected plane graph, its dual is also simple and three connected. Now I'll address the other question. In general, for graphs, duality as a concept only exists for plane graphs. Of course, you can define something else, that is a different matter. But this duality that we are talking about exists only for plane graphs. You cannot talk about the dual of an abstract graph. However, there is a more general subject, a beautiful subject called matroid theory. Fun fact, there is not a single matroid theorist in India today. But anyways, the beautiful subject called matroid theory. And for any matroid, which I'm not going to define, you can define the dual. And matroids are a generalization of graphs. And if you restrict the matroid duality to plane graphs, you will get exactly this duality. So the duality that you see in graph theory is a special case of duality in matroid theory. And using that more general theory, you can define the dual of any graph. The problem is the dual of the graph may not be a graph. It will be a matroid. And if it is a graph, that is because your original graph is a planar graph or a plane graph, right? So anyways, yeah, this is really out of scope, but there is a more general subject called matroid theory, and hopefully someday you will get exposure to that, but yeah. Okay. Any other questions or concerns while we are on this? Okay. Great. Then the dual of the dual is the original, which is unique, right? Yeah, exactly. So the fact that I mentioned that for a three connected simple planar graph, the dual is also simple three connected planar. It is also in some sense tied to the dual of the dual being unique. Yeah, anyways, let's not go there right now. Yeah. Okay, so just to give you a quick example, this graph that you had here, this is not three connected. Can somebody tell me two vertices whose deletion would disconnect the graph? Can you give me two vertices so that when you delete the two vertices, when you remove those two vertices, the remaining graph is not three connected? 0, 3 and 2, 5.
3, 5. 3, 5 also.
3, 5.
0, 2 and 3, 5.
Yeah, I think just the pair 3, 5.
Yeah, 3, 5 works and 0, 2 also works. Right?
Yes.
Okay. So that means that if I add one more edge and destroy this, then I will get a three connected graph. Here is a graph. I have added one more edge. Now this is a three connected graph. And now you cannot give me two drawings that will give me two different duals. Now this is a simple three connected graph with the yellow edge. In order to flip that, we needed that edge to be missing. Now I cannot flip this. If I flip one, I have to flip both. Okay? Anyways. Good. Looks like a prism. Yes, it is called a triangular prism. This graph is the triangular prism. It's a beautiful graph. Thank you. Good. Another drawing of this is here. This is why it is called the triangular prism. These are the same graphs. This is the same as this. Yep. Okay. Good. So now let's go back to four-color conjecture. Okay, so we have these two versions. Okay. So I want to now tell you a little bit about the history of the four-color conjecture. Yep. Okay. So as I said, the conjecture was proposed in 1853. It was finally proved, and that too controversially, in 1977. In these 124 years, and even after these 124 years, there have been multiple attempts to prove the four-color conjecture or to provide simpler proofs of the four-color conjecture. And multiple of these attempts have been failed attempts. Of course, for those 124 years, to the best of our knowledge, all the attempts were failed attempts. They were all incorrect, right? But those failed attempts still brought a lot of value to mathematics, in particular to graph theory. So I want to tell you about two of the failed attempts and give you some brief history related to those two failed attempts. Right? I will not be able to cover all the failed attempts because I don't even know them, but I will focus on two of them. Yeah. Okay. So let's start again. 1852, 53, four-color conjecture was proposed by Guthrie. One of the two Guthrie brothers, I don't know which one. Okay. And in 1977, there was the first widely accepted proof using computer assistance and, if I may add, controversial. And I'll say more about that later. This was due to Apple and Hacken. Okay. In these 124 years, there were multiple failed attempts. One of the famous failed attempts was in 1879. 1879, there was a proof attempt by Alfred Kempe, a practicing lawyer. I think it's the correct pronunciation is probably Kemp, Alfred Kemp, but I keep saying Kempe. Yeah. So Alfred Kemp gave an incorrect proof. The fact that this was incorrect was observed 11 years later in 1890. Kempe's proof, Kempe's attempt found to be incorrect. So the proof was not correct. This was by Hewood, John Percy Hewood. So Hewood found a mistake in Kemp's proof. However, using some of Kemp's ideas, and of course their own ideas, Hewood was able to prove the 5-color theorem. Hewood was able to show that I don't know about 4 colors, but hey, 5 colors definitely suffice. Okay, that also is non-trivial, but that is much simpler than 4 colors. Right? So he would also prove 5-color theorem. Okay. Another incorrect attempt, maybe I'll use a different color, was in 1880, just 1 year after Kemp's proof. There was another proof that was announced. Of course, remember, we are not in the days of WhatsApp or Zoom calls or something. So probably the other person did not even know that somebody else has perhaps proved it, or maybe not proved it actually. Right? So there was another attempt by Peter Tate, mainly a physicist, if I'm not mistaken. But of course, back then the boundaries between physics and mathematics were not so precise. Peter Tate. And interestingly, Tate's proof was also found to be incorrect exactly 11 years later in 1891. This time it was found to be incorrect by a famous person after whom the most famous graph in the world is named, called the Peterson graph. So Julius Peterson found a mistake in Peterson found Tate's attempt to be incorrect. And in doing so, Peterson also okay, so Tate's attempt was incorrect, but that doesn't mean it was useless. Just like Heawood was able to use some of Kemp's ideas to prove the 5-color theorem, in the same sense, there was something meaningful and useful in Tate's attempt. Tate gave another version of the 4-color conjecture, this time surprisingly using coloring the edges of the graph. And this equivalence is really, really non-trivial. Like the equivalence we saw is actually very straightforward. Tate's equivalence is really non-trivial. So the contribution of Tate, in some sense, the main contribution of Tate gave another equivalent formulation using edge colorings. Okay. And this actually led to a whole area of research in graph theory that is called matchings and edge colorings. Matchings being my own area of research. So this actually led to the study of matchings and edge colorings. And this started a whole branch of investigation in graph theory that actually became a major branch of investigation in graph theory for decades to come and continues to be an active area of research. Right? So that was Tate's contribution. And Peterson was the one who found. So what Tate did is Tate gave an equivalent formulation using edge colorings that was really, really non-trivial. And then Tate basically said, the equivalent formulation, of course, holds. It doesn't require a proof. And of course, like many times in mathematics, when you say something is obvious and doesn't require a proof, that is generally where all the mistakes are. Right? So, yeah, the Fermat moment, exactly. Yeah, right. So, in fact, in some sense, what Tate said was obviously true was not even true because Tate said something stronger was true. And that is not even true. And that was again found by Peterson by giving the Peterson graph as an example. Right? So I don't know if I have time to go into this equivalent formulation of Tate. Right? But what I want to do, let me see if I have time to show you a little bit about Tate's contribution. So we are at 6 o'clock today. Anyways, I cannot prove the 5-color theorem, which I will do in the next lecture on next Saturday, on coming Saturday. I'm going to have another call with all of you. So today I won't prove the 5-color theorem. Let me just show you a small part of Tate's equivalence. Okay, I will not prove the equivalence, but I will show you hopefully something that looks a bit magical. Okay, let's do it. So let's go back to our previous drawing. Maybe not this, not this. Okay, not this. I'll just make a new drawing. So let me draw this graph. Let's take a 4-face coloring of this graph. Okay, we will take a 4-face coloring of this graph. And I'm going to choose my colors. So I'll just give you some idea of what I'm going to do. We are going to take a 4-face coloring of this graph. And from that, we are going to pull out an edge coloring of the graph. Now, what do I mean by edge coloring? Color the edges so that whenever two edges have a common vertex, they get different colors. Okay? And instead of using 4 colors, we are going to use only 3 colors. Okay? Which intuitively makes sense because every vertex has 3 edges. The graph I have drawn has the property in this particular graph, of course. This graph has the property that every vertex has exactly 3 edges. So I will give you a 3-edge coloring of this graph. Okay. Yeah. Yeah, I'm thinking whether I want to do a little bit more. Give me a second. Okay, I'll do a bit more. I'm going to erase this. I'm going to start with another example. I want to show you a little bit more of Tate's thought process, which is really beautiful. If I directly start with this graph, I won't be able to show you that. So let me just erase this. Let me make a smaller graph. Okay, so let me pretend that I am Tate. Okay, for a moment. So Tate wants to prove the 4-color theorem. So let's say I take this graph, the 4-color conjecture, sorry, back then. All right. So I'm Tate and I'm trying to say that I'm trying to prove that every planar graph, I'm going to take the I'm going to take the vertex coloring version. Is that okay? Every planar graph is 4 vertex colorable. This is what I'm trying to prove. This is my graph G, and my goal is to prove that G is 4 vertex colorable. Everybody with me? Okay. Of course, I want G to be any planar graph, but I'm going to show you using an example. Okay. So now what Tate does, like many mathematicians do, they make the problem harder. Okay. So I'm going to make this problem in some sense harder, but not really. Let me explain. So what I will do is I will make a copy of this graph. Let me clone this and let me also, actually let me make it smaller. It's too big. I will regret my choices later. So let's make it smaller. Is this visible? Okay. So this is my original graph. Now let me clone this fellow. So this is my first step. I'm going to make this problem harder by adding more edges to this graph. Do you all agree that I can add more edges to this fellow and still keep it a planar graph? Yeah? Okay.
Yes.
Can someone tell me how many more edges can I add to still keep it planar?
4, I think.
You
Yeah,
are
I
close.
think
Try it on your piece of paper. See if you can actually add 4.
Two to we
I
can't.
can add 3.
Between
Oh wait, we
two
can't
of the
do 2
rectangle
because the
vertices.
diagonals will
So
intersect.
2 for
Yeah.
sure. Let me add 2. Let me first add 2.
Then diagonals
I
will
will add
come
this
check.
and I will add this. Can I add
One
any
from the outside, connecting the two.
outside
right.
face? Don't forget the outside face. Good. So now I add one more. Of course, I could have added different edges, but I'm deliberately choosing some edges. Doesn't really matter. Okay. So what I will do is I will make my life harder by adding more edges. You all agree that this makes life harder in some sense? But of course it doesn't, because I want to prove that every planar graph is 4 vertex colorable, right? So in some sense it doesn't actually make it harder. I mean, I still need to show that this graph is also 4 vertex colorable. Okay. So this is called a maximal planar graph. Now I cannot add any more edges. Of course, here I am adding edges. I'm not looking at multiple edges. Of course, you can add multiple edges, you will get a planar graph. But I cannot add any more new edges joining non-adjacent vertices. Okay. And the reason for that is now every face, the boundary is just a 3 cycle. This is essentially the reason we are not able to add any more edges. Okay. Good. So instead of coloring the original graph, I will color this graph. Let me call it G tilde. Okay. I added more edges, but I still want to keep it planar. So now the new goal is revised goal. This was the first goal. Now the revised goal is G tilde is 4 vertex colorable. By VTX, I mean vertex. Okay. So if I prove that this graph is 4 vertex colorable, then of course this graph is 4 vertex colorable. You all agree?
yes.
Good. Okay. Now what we will do is, now we will take the dual of this G tilde fellow. Now can you tell me, in this G tilde, what will the degree of each vertex be in the dual of G tilde? So now I'm going to draw the dual of G tilde. Let me put an arrow. G tilde star. What will the degree of each vertex be in this fellow? 3. The degree of each face. By degree of a face, I mean the number of edges in its boundary. Okay. The degree of each face here is 3. That now becomes the degree of each vertex here. So the dual is what is called a 3 regular graph. Okay. So what I get is a 3 regular graph. I'm also going to use some facts that I did not prove. Maximal planar graphs are are 3 connected. Okay, so this is actually a 3 connected graph. That is something one can prove, that any maximal planar graph, so you have added as many edges as possible. Now your graph will actually be 3 connected. Okay, so the dual will be a 3 regular, 3 connected, and of course the dual is also planar, right? So it is a 3 regular, 3 connected planar graph. Okay, there are some facts we have not proved, but I hope you can just believe me on those. Okay, so now, but we wanted to color the vertices here. So what should we be coloring here?
The faces.
Faces. We will take this as a plane graph actually. We will actually take this not just as a planar graph. I will take it as a plane graph because I can get a drawing which is in which no edges will cross. So I can color the faces of this fellow. So now my third goal. This graph, if I prove that it is 4 face colorable. If I prove that this graph is 4 face colorable, then I get a 4 vertex coloring of this graph, then I get a 4 vertex coloring of this graph. You all agree with me? Good. So we now have one more version. Instead of proving all plane graphs are four-phase colorable, I will just prove that all three regular, three connected plane graphs are four-phase colorable. If you prove that all three regular, three connected plane graphs are four-phase colorable, then you have proved the four-color conjecture. We are not yet in edge coloring, okay? We will still go to edge coloring. Okay, so let me write one more version of the four-color conjecture. Four-color conjecture. Instead of looking at all plane graphs, I will just look at every three regular, three connected plane graph is four-phase colorable. Look at the irony of what we have just done. The original version said every plane graph is four-phase colorable. Then we used duality to make a vertex coloring version of it. Then we added more edges, and then we again used duality to go to phase coloring. But now we just have three regular, three connected plane graphs instead of all plane graphs. Yeah? Fun times. So to prove the four-color conjecture, it suffices to prove this statement. Yeah? Great. Let me draw the dual actually. So let me select this because I still need to go to edge coloring. So, okay, I got this fellow. Actually, let me not select everything. Let me just do this again. Just this part. Okay. Clone. Okay, good. Now let me draw the dual. Right, so this is not the dual. I will draw the dual in another color. Maybe I will use the blue color. Okay, good. I know what the graph is, so I'm drawing it in a certain way. Okay. Does everybody see the blue colored graph? Not a very pretty drawing. I will make a prettier drawing. I would like you all to check that this is the same as the blue colored graph is exactly this graph. The cube graph in this example. Yeah. Okay, thank you.
Yeah.
Okay, so that means that for this example, if I can show you a four-phase coloring of this fellow, then you will get a four-vertex coloring of this fellow. Okay, good. So now we have a three regular, three connected plane graph. And we want to color the faces using four colors. Now what we will do is we will actually convert this into an edge coloring version. I will show you one direction of Tate's theorem. It's proof actually. Whatever I'm doing is actually can be converted into a rigorous proof that works for all plane graphs. Okay. So we will show that if this graph has a four-phase coloring, then it also has a three-edge coloring. Okay. So this is what we will show. To show this graph, this is G tilde star. If G tilde star, think of this as any three regular, three connected plane graph. Okay. We will not necessarily use all the properties. Right. I will not explicitly use three connected. In fact, the statement is also true for two connected, which is simpler to think about. If G tilde star is four-phase colorable, then it is also three-edge colorable. Okay. Before we do this, I want to ask you all a question. I was told by Sai that you all have seen some matchings, maybe Hall's theorem or something. Have you seen Hall's theorem?
We had couple of classes on Hall's theorem. Yeah.
Yeah.
Great, great,
Yes.
great. Okay, good. So you all know Hall's theorem, or at least you have heard of it. Okay. If you know Hall's theorem, then you know what a matching is, and you perhaps also know what a perfect matching is. Yeah, great. If you know what a perfect matching is, great. Otherwise, let me quickly show you a perfect matching of a graph. I will take another graph maybe. Oh, I already have the graph here. It's fine. I'll just draw it here. Perfect matching is something that looks like this. Every vertex has degree 1. In the pink colored graph, if you just take the pink colored edges, you have a graph in which every vertex has degree 1. That is called a perfect matching. Another way to think of it is every vertex has been matched by a pink colored edge to another vertex. This is where the word perfect matching comes from. Yeah. So what I want you all to do is I want you all to think about 3-edge coloring this graph and see if you can relate it to perfect matchings. Oh, I'm not going to use Hall's theorem at all. There's a comment saying that we can prove something without using Hall's theorem. We won't use Hall's theorem, don't worry. Yeah. Yeah, maybe it was better, I think. So can you explain what you were thinking?
So I was just worried because you said we are going to prove this, and then you asked whether we are going to use Hall's theorem. But I
Oh, no,
thought,
no, no. I was checking about Hall's theorem only to see whether people know what matchings are.
oh,
We won't use Hall's theorem. In fact, this graph need not even be bipartite. Although here it is a bipartite graph in this example. In general, this graph may not be bipartite, and Hall's theorem is only applicable to bipartite graphs. So yeah, what I wanted to make sure is people know what a matching is and what a perfect matching is. And now what I want you to do is I want you to think about 3-edge coloring a 3-regular graph. 3-regular. I want you to think about 3-edge coloring a 3-regular graph and tell me if that has something to do with perfect matchings. Supposing you yeah, go ahead. Yeah.
So can you again redefine the edge colorable thing?
Okay, I'll define it. Yes. Whenever 2 edges share a vertex, they should get different colors. That's it.
Okay.
Whenever 2 edges have a vertex in common, their color should be different. So now can you all think about this? If I give you a 3-regular graph and I tell you that it is 3-edge colorable, can you now phrase this in terms of perfect matchings? Look at a vertex and think about what you will see at that vertex. Okay, I see one of you can at least has already seen it based on your head nods. So think about your 3 colors as being red, blue, and green. Supposing I have, right, at every vertex I have 3 edges because it is a 3-regular graph. Supposing your 3 colors are red, blue, and green, then what can you say about the red edges?
They have to be a perfect matching.
The red edges form a perfect matching. The blue edges form a perfect matching. And the green edges form a perfect matching. So you have 3 disjoint perfect matchings. So saying that a 3-regular graph is 3-edge colorable is the same as saying that it has 3 disjoint perfect matchings. This is at least one point in history where people started studying perfect matchings and matchings. Right? So saying that it is 3-edge colorable is equivalent to saying has 3 disjoint perfect matchings. Yeah. Let's look at one example. I will color this graph. I use the pink color. I will use blue color. And I will use one more color for the remaining edges, maybe green color. This is a 3-edge coloring of this graph. This is a 3 regular graph. And the 3 colors, each of them is a perfect matching. Okay, so this statement is basically a statement about perfect matchings. Yeah. But we will not use the matching viewpoint. We will directly go from a face coloring to an edge coloring. And then we will argue that it is actually a 3-edge coloring. Okay, so this is what I want to show you next. If a 3 regular 3 connected plane graph is 4 face colorable, then it is also 3-edge colorable. Okay, so what we will do is we will take a 4 face coloring of this graph, and from that we will pull out a 3-edge coloring of the same graph. Yeah. Okay, everybody with me? Are there any questions or concerns before we proceed? Okay, if not, let me take a 4 face coloring of this graph. Remember, this is our graph G tilde star. Yeah, that is how we came here. So I'm going to take a 4 face coloring, and I'm going to use the colors 0, 0, 0, 1, 1, 0, and 1, 1. Okay. But I will of course use colors also. So let me say 0, 0 is green. Let me say 0, 1 is pink. 0, 1. And I can also use 0, 1 here. Let me say 1, 0 is orange. And of course, I can use 0, 0 outside, but for the sake of diversity, let me also use the 4th color. So the 4th color, what should I choose? Maybe I'll choose red. I'm going to call it 1, 1. Yeah? Do you all agree? This is a proper 4 face coloring of this graph.
Yes.
Great. Now what we will do is, we will somehow define from here an edge coloring of this graph. Okay? So I want you to observe one property, which is actually true for any 2 connected plane graph. If you look at any edge, there is one face here and there is another face here. On one side of the edge, you will see one face. On other side of the edge, you will see another face. This property is true. These are different faces. This property holds for any graph that does not have so-called cut edges. By cut edge, I mean an edge like this, whose deletion disconnects the graph. Okay? So this cannot happen in a 3 connected graph. In fact, it cannot even happen in a 2 connected graph. Okay? So we are going to use this fact. For this edge, E, I am going to look at the color of this face, F1, and the color of this face, F2. And I'm going to use the colors of F1 and F2 to define a color for the edge E. Yeah. Any suggestions on how we can do this? There might be many ways to do it, but what is one nice way to do it? Better, yeah.
Yes, we take XOR.
XOR. Yeah, you all like XOR? Symmetric difference is the same as XOR. So we'll do XOR. Yeah. Let's XOR the 2 and see what we get. Okay. So maybe you all can tell me for each edge what the colors are. So what is the color of this edge?
1, 1.
1, 1. 1, 1 is red. So let me just color it red. 1, 1. Yeah? Okay. What about this fellow?
1, 1 again.
Also 1, 1.
Yeah.
about this fellow also 1, 1. And this fellow also 1, 1. Yeah?
It's perfect matching also.
This is a perfect matching. Good. Okay. Now let's look at some other edges. Let's look at the 0, 0 and 1, 0. What will I get?
1, 0.
1, 0. Orange. This is 1, 0. And same thing happens here. Is it? Where else do I get 1, 0? Maybe this one and this one, right? This is 0, 1. And this is 1, 1. Does that give me 1, 0?
Yes.
So do you all agree that this is also 1, 0? And perhaps this is also 1, 0? 0, 1 and 1, 1. 1, 0?
Yeah.
Let's finish the last 4 edges. Why not? So let's look at this edge, the bottom edge. What is its color?
0, 1.
0, 1.
0, 1. 0, 1 was pink color. Okay. This is 0, 1. What about this fellow? It is also 0, 1, is it? Yeah. This one is also 0, 1. And this one is also 0, 1. If it feels like magic, it is supposed to. But of course it is not. And I don't know. What is magic? Anyways. Right? So do you all agree that what you got is a proper 3-edge coloring of this graph? At every vertex you see one pink edge, one red edge, and one orange edge at every single vertex. That's just a 3-edge coloring or 3 disjoint perfect matchings. This is actually how you prove it. Of course, you need to now argue why this is a 3-edge coloring. Why is it true that at every vertex you see 3 different colors? I will leave that to you. This method also gives converse. Not sure what you mean. Anyways, you can think about it. The converse is actually not so easy. The converse is significantly more non-trivial. You can try working on the converse. What Tate proved is that it is actually if and only if. I'm not going to do the converse in the interest of time. So actually this statement is not an if-then statement. It is an if and only if statement. And the converse is actually significantly more non-trivial. It requires some different way of looking at things. I don't know how to directly convert this proof into the converse proof. Intuitively, it makes sense because intuitively it seems that pulling out 3 colors when you are given 4 colors intuitively seems more easy. Pulling out 4 colors from 3 colors seems like you have too little information and you are still able to pull out 4 colors. That intuition, I think, is actually correct. The converse, in some sense, is actually trickier. Not that this was also trivial. We had to choose the colors to be 0, 0, 0, 1, 1, 0, 1, 1, and then we have to do the symmetric difference. And then you actually have to prove that this is a 3-edge coloring, which I'm not going to do. I'm going to leave it to you as an exercise. Right? So you all can think about it, why this works. Right? And if you can't get it, then you have my YouTube channel, you can go through it. Right? But try it out. The point I want to mention is Tate made a beautiful contribution. Tate gave an edge coloring version of the 4-color conjecture. And maybe I want to add a few more points. So a 3-regular graph in general need not be 3-edge colorable. What is true is every 3-regular graph is either 3-edge colorable or 4-edge colorable. This is well known. It's essentially famously called Wissing-Gupta theorem. So Wissing proved in 1964, Gupta proved in 1966. So every 3-regular graph You can either color the edges using 3 colors or color the edges using 4 colors.
Is there a difference between if it's 3 connected or it's not? Does that what makes a
For a
difference
3
between
connected
3 and
3
4?
regular graph,
Yeah.
you can either color it using 3 colors, but there are 3 connected 3 regular graphs that are not 3-edge colorable, and the smallest such graph is the Peterson graph.
Right. Okay.
Yeah, since we talked about Peterson, let me go back to the previous page, the history page, and let me write down one of Peterson's contributions is maybe I'll use another color. Peterson discovered the Peterson graph, and this is the smallest 2 connected. You don't even need 3 connected. It is the smallest 2 connected 3 regular graph that is not 3-edge colorable. Let me actually draw the Peterson graph because maybe some of you don't know. I'll quickly draw the Peterson graph. It's beautiful. This is the Peterson graph. This is the smallest 2 connected 3 regular graph where you cannot color the edges using 3 colors. You need 4 colors, and 4 colors suffice.
It's like taking a K5 and every vertex on it, you pull it out and take the pentagon around it with you.
Yeah, another way to say that, yeah, so I'll rephrase what you just said. You can take this perfect matching of the Peterson graph and you can squeeze each edge into single vertex. What you will get is K5. This operation is called edge contraction. If you contract all the edges of a perfect matching in the Peterson graph, any perfect matching in the Peterson graph, you will get K5. And this is actually very nice because to prove that this graph is not 3-edge colorable, you actually have to use this cut. What is a cut? Take the vertex set, break it into 2 parts, and look at all edges going from one part to the other part. That is called a cut of the graph. So using this cut that separates the outside 5 cycle from the inside 5 cycle, you can actually prove that this graph is not 3-edge colorable. Okay? Good. All right. So there is a nice quick point I want to mention. The 2 connected 3 regular graphs that are not 3-edge colorable. There's a beautiful name for these graphs. 2 connected 3 regular graphs that are not 3-edge colorable. They are called snarks. Snarks comes from Lewis Carroll's poem, The Hunting of the Snark. And the name was given by Martin Gardner, who some of you may know, was one of the main US American mathematicians who popularized mathematics especially amongst younger people and got them interested in mathematics. So this name snarks, of course, is because of Martin Gardner, because clearly he was more creative than most mathematicians in some regards. So yeah, he came up with this name, snarks. And recently, I and my PhD student Santosh, we attended a workshop on snarks in Paderborn in Germany for 4 days. So that is why I wanted to also mention this. The whole workshop was just about snarks. It was beautiful. It was fantastic. Anyways, so these are snarks. And the Peterson graph is the smallest snark in the world. Yeah. Okay.
Can you, sir, redefine again? Tell what did snarks actually mean?
Can you repeat the question?
Can you actually tell what again snarks actually mean?
Yeah, snark is any 2 connected 3 regular graph that is not 3-edge colorable.
Okay.
Yeah. So you generally put 2 connected because otherwise you can make smaller examples. And anyways, in Tate's theorem, you will get 3 connected graphs. So typically, this is a common definition of snarks. In some definitions of snarks, people impose more strong connectivity conditions, but this is a technicality, so I will skip it. The most popular definition is perhaps this one.
Sir, are there arbitrarily large snarks?
Oh, yes, beautiful. Yes. So for a long time, people thought that maybe there are not too many snarks in the world. In fact, for a long time, Peterson was the only snark known to people. Then they found, so Peterson has 10 vertices. Then the next smallest snark has 18 vertices. If I'm not mistaken, there are 2 snarks on 18 vertices. For that, you need to make the definition slightly stronger. So what you can do, here is a silly thing you can do. You can take a vertex of the Peterson graph and replace it by a triangle. And this will again be a snark. So certain definitions of snarks, which is I would say the more technically common definition these days, they don't allow cuts of size 3. If I have a cut with exactly 3 edges, then what you can do is you can get a smaller snark from it. So modern definitions of snarks generally forbid these kinds of cuts. Of course, you will have single vertex where 3 edges are incident. This is also a cut, but here neither of the sides is a single vertex. One is a triangle and one is a larger graph. So these are called essentially 4-edge connected 3 regular graphs. And if you put this condition, then the next snark has 18 vertices. So directly from Peterson graph 10 vertices, you go to 18 vertices. People conjectured at some point, maybe there are finitely many snarks with this more technical definition. And eventually people actually disproved it. There are indeed infinitely many snarks, just like there are infinitely many prime numbers, if you like. Okay, so there are indeed infinitely many of them. In fact, we don't know of any sort of complete characterization of snarks. Right? So even the infinite families people have found, then somebody will find a snark that is not in any of these families. Does this method guarantee more snarks? Who could have? Lewis Carroll was a mathematician before he was a writer. Yeah. Who could have thought of this? Does this method guarantee more snarks? Which method? Yeah, I don't know. Oh, point to triangle. Yeah. So using this, converting a point, a vertex to a triangle, you can make lots of snarks. But that is why people put some additional conditions on the definition of a snark. But even with those additional conditions, there are infinitely many snarks. Okay.
Aren't there 5 cuts in the Peterson graph?
Which cuts? Peterson graph has 5 cuts. That is okay. What they will not allow is 3 cuts.
Oh, exactly 3 cuts. Okay.
Exactly 3. Of course, the single vertex 3 cuts will always be there, but they don't want other 3 vertex cuts. For example, this graph, the triangular prism that we drew earlier, this graph has a 3 cut, where neither of the 2 sides is a single vertex. So this is not essentially 4-edge connected. In the Peterson graph, you cannot find such a 3 cut. The only 3 cuts in the Peterson graph, they are all like this, single vertex. Okay, so this is called essentially 4-edge connected, when you don't allow 3 cuts that are different from single vertex cuts. And if you put this essentially 4-edge connected, then the next snark has 18 vertices after the Peterson graph. And then if I'm not mistaken, there are more snarks on, I'm not sure about 20, but I think on 22 or 24 vertices, there are more snarks. And yeah, people have actually created whole databases of snarks. If anybody is interested in snarks, you can check out a beautiful website called House of Graphs. This is maintained by one of the people who maintains it is Jan Goedgebeer from Belgium. Goedgebeer. He's from Belgium. He's a good friend of mine, and he was recently at the snarks workshop in Germany. So they maintain full databases of snarks that are known to graph theorists today, right? And the list keeps getting larger and larger, but computers Don't scale up so fast. Yeah. Good. Any other questions or concerns? Okay. So since we are already at 6:47, I presume I'm stopping at 7 o'clock. Is that correct? Yeah, 7 o'clock. Okay. So what I will do is I will just give you a brief outline of what I am planning to or hoping to cover in the next lecture. And I will also quickly summarize what we did today because I think I gave you a lot of information. So sorry about that. But I'll just quickly summarize what we did, what are the main points, and what we will do next time. Is that okay? Okay. Before I do that, any other questions or concerns? Okay, good. So let me just do a quick summary of what we have done today. Let me just go to the previous pages. Right, so we started with the four-color conjecture. We looked at the original phrasing by Q3. In fact, I also need to complete the history, so I'll do that. We looked at the phrasing by Q3. Then we converted into a graph theoretical statement, which is the face coloring version. Every plane graph is four-face colorable. And then we discussed duality, plane duality, and we phrased it in vertex coloring. Every planar graph is for vertex colorable, right? Two versions. This equivalence is actually quite straightforward, right? Once you figure out duality, it's not too difficult to see this. Okay. However, there are other beautiful equivalences. But before we go there, before we summarize that, let's complete the history really quick. So it was proposed in 1852-53. In 79, there was an incorrect attempt by Kemp, and this incorrect attempt was used by Hewood to give a proof of the five-color theorem. This proof we will see in the next lecture for sure. Okay. And there was another incorrect attempt in 1880 by Peter Tate, and this was found to be incorrect by Peterson, right? However, Tate, the one very beautiful contribution of Tate was to give an equivalent formulation using edge colorings. So we looked at the edge coloring version, which is here. We observed that the four-color conjecture is equivalent to proving that every three regular three-connected plane graph is three-edge colorable. This is called the edge coloring version. Okay, and of course we only saw one direction using an example. You can prove it rigorously yourself, you can try it. And the other direction is actually harder in my opinion. But both directions proofs are available on my YouTube channel. If you get interested, you can go and check it out, right? So that's the edge coloring version, which is basically nothing but saying that there are three disjoint perfect matchings in any three connected three regular planar graph. So that also leads to the matching theory and edge colorings as areas of research in graph theory, right? And now let's come back to the history. So we got the edge coloring version in 1880 due to Tate, right? And then there were probably many other incorrect attempts that I am not very aware of. I don't know how significant they were. These were very significant. In 1977, a so-called correct proof was proposed, was given by Apple and Hacken. This was a computer-assisted proof. It was pretty controversial and continues in some sense because, well, there are many people who are not too fond of computer-assisted proofs. For that matter, myself, I would love to see a proof that I can actually teach, if not online, at least in person. If not in one lecture, at least in one semester, right? But I don't think that is that easy. So this proof, there were actually people who found mistakes in the proof, and they wrote to Apple and Hacken, and they corrected most or all of the mistakes. But the proof had something like 1800 cases, and these 1800 cases were humanly impossible. So that is why it was computer assisted, right? And eventually in 1997, Robertson, Sanders, Seymour, and Thomas, they gave another computer-assisted proof. This was simplified compared to Apple and Hacken. Apple and Hacken had some 1800 cases. Robertson, Sanders, Seymour, Thomas has something like 600 cases. Okay, but it's still 600, so good luck. I have never gone through those cases, nor do I intend to go through them anytime soon. So if you ask me, have I ever seen a proof of the four-color theorem? The answer is no. Right? To actually go through the whole proof, I think I would need a lot of time, which I'm not really willing to invest because I have other things to work on. I have other mathematical problems to solve and other things to do. Right? So it is also a computer-assisted proof, and that's the best we have got so far. So there is no known proof of the four-color theorem that I could actually deliver to you in a few video lectures. And that is pretty dissatisfying and unfortunate. So the question remains, is there an elegant proof? Whatever elegant means. Right? So that we don't. Anyways, so that's the history of the four-color conjecture. By the way, the person who taught me graph theory first is Robin Thomas, who unfortunately passed away a few years ago. So anyways, yeah, so that's the history. And in the next define elegant, I won't do that. Yeah, so in the next lecture on coming Saturday, which will be 13th of December, we will see first a proof of the six-color theorem, which is actually quite easy once you prove that every simple planar graph has a vertex of degree at most 5. So we will prove this, and as a do-it-yourself exercise, see if you can complete the proof of the six-color theorem yourself. Assume that every simple planar graph has a vertex of degree at most 5, and see if you can finish the proof of the six-color theorem. Okay? But this method does not extend to the five-color theorem. So to prove the five-color theorem, we will need more sophisticated ideas that basically come from Alfred Kemp. So that's all for today, but I'm happy to take questions and discuss for a few minutes. Yeah, thank you. What was my PhD on? My PhD was on structural graph theory, in particular on perfect matchings, or more generally matching theory. And my thesis is available on my webpage. You can check it out. Thank you. And my PhD was with USR Murthy, who has written the famous textbook on graph theory, Bondi and Murthy. Unfortunately, Professor Murthy also passed away earlier this year. Any other questions, concerns, discussions? Do you intend to tackle any mainstream problem anytime soon? What is a mainstream problem? Define that. So, I mean, I can give a very long answer to this, but in the interest of time, I'll keep it short. Combinatorics continues to receive very poor treatment in India. This was the case back in the day, even in many other countries in the West. When Bill Tutt did graph theory, a lot of contemporary mathematicians laughed at him, saying that graph theory is just some recreational mathematics. But Bill Tutt kept doing it. Today in UK, Canada, many other countries in the West, graph theory, combinatorics are very, very well respected subjects. Unfortunately, that continues to remain a bit elusive in India. Things are changing. So whether combinatorics is mainstream mathematics or not, it depends a lot on the country you are in. And hopefully in a few years, combinatorics shall be mainstream mathematics in India. We'll see. I intend to continue working in combinatorics, in particular in graph theory, in particular in matching theory. Yeah. Yeah, I think this whole what is mainstream mathematics or not is very, very subjective, and it is actually used to discriminate against various forms of mathematics. So yeah, I think I'm not a big fan of this sort of hierarchy because if combinatorics is that easy, please give me a proof of the four-color theorem that I can teach in a lecture. Right. So, anyways. Okay. Anyways. Yeah, I intend to continue working in graph theory. To me, that is already mainstream mathematics. But yeah, anyways, any other questions? I'm happy to talk about these things more in detail. It's just that I have another meeting starting in a few minutes, so I'm not going into a rant about combinatorics and its treatment in India. Yeah, but I think I did engage in such a rant when I went to CMI. Okay, any other questions, concerns? Um, all right, if not, I'll see you all on coming Saturday. And do I intend to take more classes? No, it's a bit difficult because I am really packed with a lot of students working on research, and teaching will start again in January. So yeah, I would love to, but it's just yeah, I don't really have much time. So I agreed with Sai. She had asked me after the IMOTC at CMI whether I could do some online lectures. So I told her that, look, during the semester, I'm too busy teaching my main course that I'm teaching at IIT Madras, but I can do it in December. So that is why she contacted me in December, and I'm like, yeah, well, as I promised, I will definitely do it. But then I realized that to really do justice, I need at least 2 lectures. So I agreed to 2 lectures. But yeah, most likely I won't be doing more in this December, but maybe next December or maybe the summer break. And in general, of course, I would love in-person lectures more. So if it is possible to do something in person, that would be a lot more fun. Yeah, online is not that much fun, right? It would be nice to have you all in person, but I understand it is not easy. Okay, good. Any other questions or concerns? All right. If not, I'll see you all on Saturday. And in the meantime, if you have any questions or concerns, you can make a list of them and even send it to me in advance. And I will try to address those in Saturday's lecture.
Thank you for the class, sir. Bye.
Thank
you
you
very
for the
much.
class.
Bye.
Thank you.
Thanks
Look
for
forward to
teaching.
the
Thanks
lecture on
everyone for
Saturday.
attending, and have a nice weekend or remaining
Thank you, sir.
Sunday. Yeah. Okay. See ya. Bye.
Bye. Bye.
Thank you.
Thanks.